A pleasant day, everyone. Welcome once again to our discussion. Today, we are going to discuss about continuity. But before we go to the topic, let's have a brief recap of what we had last discussion about limit at infinity. Okay, so I want to just remind everyone of what is the important things that we need to emphasize a little bit uh, yesterday. Okay, so we have this last time. I give you these exercises. I hope you have solved them already. So it will be a very helpful for you for our coming quiz number 1 next week. All right, so geometrically, when we speak of limit at infinity, so we have here the line given by y equal to L is a horizontal asymptote of the graph. Horizontal asymptote of the graph of f of the function if at least one of the following is true. Alright, so what is this? So the limit of the function of x as x approaches to positive infinity is equal to L, or the limit of a function of x as x approaches to negative infinity is equal to L. Okay? Then from the infinite limits, the line given by x equal to a, so this is the vertical asymptote. Okay, so the line given by this equation x equal to a is the vertical asymptote of the graph of f if at least one of the following is true. Okay, so these are four possible result that the limit of a function of x as x approaches to a from the right. Okay, so the positive here means from the right equal to positive infinity, or the limit of a function of x as x approaches to a from the left equal to positive infinity. Or it can be that the limit of f of x as x approaches to a from the right is equal to a negative infinity or equal to negative infinity for the limit of a function as x approaches to x from the left. Okay, so just remember this two important principle. No? We speak of geometrically. So y equal to L here is the horizontal asymptote. No? Horizontal asymptote of the graph. Okay? Alright, so we have here an example. Rational function f of x equal to 2x plus 4 divided by x minus 1. So if you're asked to find the horizontal asymptote, find the horizontal asymptotes and the vertical asymptotes of the graph of f and sketch the graph. Okay, so you have to graph this one and see the vertical and horizontal asymptote. But for the horizontal asymptote, the vertical asymptote, this is already very clear that it is the value of x that can make the denominator equal to 0. So what that value is that? Or what value is that? So x equal to positive 1. So when x equal to positive 1, so positive 1 minus 1 equal to 0. So that value of x equal to positive 1 is the vertical asymptote of this function or the graph of this function. Okay, so I think that's all class that you need to remember about horizontal and vertical asymptote. Now, we'll go to our main topic for today about continuity. So what does it mean, continuity? So we're talking of functions. So what is this continuity means? So continuity at a number. So we're talking of continuity at a number. Alright? So a function f is continuous at the number a, okay, a certain number a, if and only if the following three conditions are satisfied. So we have three conditions here to test whether our function will pass through these three conditions. So what are these conditions? So first is we have the function of a, meaning the value of or the value of the function at x equal to a exists. Okay, so that is the first condition. The second condition is that the limit of the function of x as x approaches to a exists. So it means that you need to determine the limit of f of x as x approaches a from the left, and also the limit of f of x as x approaches to a from the right. And we know from the condition to make the function exist, their limit must be equal. The left hand limit and the right hand limit should be equal. Alright, so that's what we had to, or we have to remember this condition. And then the third one is that the limit of a function of x as x approaches to a equal to the value of the function at x equal to a. Okay, so once all these conditions are satisfied, then we can say that the function is continuous at the number a. So if one of these conditions fails to hold at a, okay, at this value at a, at a number, then f is said to be discontinuous at a. Alright, so just remember this. So the procedure here is that you have to substitute the value of a to the function and then solve for f of a. Next, you have to find the left hand and right hand limit for this, and then you compare. If they are equal, then the limit of this is equal to that same value. Okay, limit from the left, limit from the right. And then here you have to compare the limit of f of x as x approaches to a, if this is equal to f sub a. If this is equal to f sub a, therefore, so all these conditions are satisfied, so we can say that the function of f continuous at that number a. Okay, so let us take this first example. We have three examples prepared here, but I just want to solve one of them, and then I want you to practice the next two numbers. Okay, so listen carefully, class. This is a very important topic. So we're given here f of x equal to x squared plus 1. Our function of x is equal to x squared plus 1. And now we are asked to determine if the function f is continuous at x equal to a, or x equal to 2. And the other one, we have to determine if the function f is continuous at x equal to minus 1. Okay, so first we have to test. Now we have to test these three conditions. Number one, we have f sub a. So we have to find if f sub a exists. So we're given f sub x equal to x squared plus 1. Okay, so for the first requirement, to determine if the function is continuous at x equal to 2, so we have to use this number. So this is our a. Alright, 2 here. This is our a as mentioned in the concept in the previous slide. So therefore we have f sub a. So f sub a, where our a is equal to 2, so f sub 2. Okay, so you just substitute the value of 2 to this equation, or this expression, x squared plus 1. So our x is equal to 2, so 2 squared, okay, plus 1. This is equal to 4 plus 1 equal to 5. Alright, so it means that f of a, which is f sub 2, or f sub 2 here, which is our f sub a, exists. Okay, so we have a value here which is equal to 5. Alright, so it means that condition number 1, okay, we passed condition 1. So condition number 2, okay, so condition number 2 is that the limit the limit of f of x as x approaches to a, where our a here is equal to 2. So, alright, so then rewrite it as the limit. So substitute the values, so or the expression of our f of x. So instead of f of x, so you write x squared, plus 1. Then you enclose this with the parentheses, right? And then as x approaches to a, where our a is, in our first problem is, this is our a, which is equal to 2. Okay, and now we have to test if this one has a certain value. Okay, so if this one exists. Okay, so to test this one, we need to find out if the limit of x sub 2, or sorry, x squared plus 1 as x approaches to 2, and that is from the left. Okay, so equal to. Now before we can do this class, I think we need to graph the function first. Okay, so to graph, we have here we have x, then we have f of x. So it means that we need to assume values for x, and we need to assume we need to solve for f of x. Okay, so in our number line, assuming this is our number line, so assuming this is our 0 here, okay, so we have x equal to 1, 2, okay, so this is our x-axis, this is our infinity, no, towards the right, and then towards the left we have negative infinity. Okay, so we have here negative 1, negative 2, and then we have negative 3. Okay, so we just balance this one. We have, you can put as many number as you want plus. Okay, and then we just ready our x and y coordinates here, no, for our drawing, or for our graph. Okay, so I'll just draw the vertical first. This is our y-axis. Sorry, it's not. Okay, so let me draw it a much better, a little bit straight. Okay, so assuming that is our y-axis and this is our x-axis. And this is our y-axis, which is a function of x. Sorry class, I have to stop here. I want to make the graph first. Okay, and then we'll label this one as 1, and we have here 2, we have here 3. On the other side we have negative 1, negative 2, and just extend a little bit here. We have here negative 3. Then we label this one as 1, 2, 3, these are 4. So I know the value that we need to use class, so that's why I just put it right away. So 5, 6, then 7. So this is 6, 7, we have 8, we have 9, and let's just stop up to this part here. Okay, and then let's continue this. So when x equal to negative 3, just look at our number line. So when x equal to negative 3, what is our f of x? What is our f of x? So when x equal to negative 3, so we have f of x. We just substitute this to our function. So when x equal to minus 3 squared, so that is positive 9 plus 1. So this is 10. Okay, so when x equal to minus 2, okay, so just refer to this graph class or this Cartesian coordinates. So when x equal to minus 2, so when this is minus 2 squared is 4 plus 1, so we have 5. And when x equal to minus 1, so our f of x is, if this is minus 1 squared is positive 1 plus 1, so this is 2. When x equal to 0, so when x equal to 0, so what is our f of x? So if this is 0 squared is 0 plus 1, so this is 1. Okay, so let's continue this. Sorry. Okay, so when x equal to 1, so what is our f of x? So 1 squared is 1 plus 1, so this is 2. When x equal to 2, so when x equal to 2, so 2 squared, 4 plus 1, 5. When x equal to 3, so when 3 squared 9 plus 1, so this is 10. Okay, so before we continue this one, so that I can explain it to you clearly, so we have to make the graph first, graph of the function. Alright, so let us plot the points. Alright, so we have here, if x equal to minus 3, our f of x equal to 10. Okay, from minus 3, you just extend a line towards, just go 10 times upward. Alright, so this is now our point. Okay, I'll change the color. Okay, so let's use this color here. This one. So, okay, the point is here. When x equal to minus 3, f of x equal to 10. When x equal to minus 2, f of x equal to 5. So when minus 2, go up to 5. Okay, so we have here at this point, approximately somewhere here. When x equal to minus 1, so f of x equal to 2. So when minus 1, f of x equal to minus 2. So it's somewhere here. Okay, so when x equal to 0, so when x equal to 0, f of x equal to 1. So it means here, 0, x, this is origin, 0, 0. So x is 0 here. So our f of x is equal to 1. Okay, so up to this, it's at this point. Okay, now when x equal to 1, f of x is 2. So when x equal to 1, f of x is equal to 2. Then when x equal to 2, f of x equal to 5. Okay, so 5, it's somewhere here. When x equal to 3, that is 10. Okay, so It's somewhere here. Now we know that to graph or to sketch the graph, we need to simply connect the points, right? So just connect the points. So connecting the points, so we will have this graph. So from this point, so draw it down, connecting the points. Okay, so this is our graph, and you can extend this one. So it may, and then put an arrow, so to indicate that you can add more values for x here to the right and also to the left. So you can just extend this and then put the arrow. Okay, so now let's continue this discussion here. Okay, so as mentioned, to prove that the limit of f of x second condition as x approaches to a, it should exist. So we have to test. No? For this case, we have limit of x squared plus 1 as x approaches to 2. So we need to test, no, the limit of x squared plus 1 as x approaches to 2 from the left. Okay, negative here means from the left. It means, class, that we need to trace the graph. Okay, so we need to trace the graph from the left towards the point or to the values of x that it approaches to. Okay, so in this case, the condition is, or the problem is to determine if the function f is continuous at x equal to 2. So where is our x equal to 2? So this one. Okay, so it means that we have to make this. Okay, let's do this graph. I mean, there's vertical line. Okay, so it means, class, that we need to trace this graph from the left towards the right. So if it means that every time you move this one, every time that you move this, it means that your value or the value of x is changing also. So from the left, one-sided limit, if you can still remember, so from the left, it means that the values of x is increasing. Okay, increasing siya, class, in a sense that this is a negative number. If the negative number is getting smaller in value and getting closer to 0, so it means that the number is increasing. Okay, so our values of x, as we trace the curve going to the right, okay, so from this point, for example, okay, so trace the graph going to the right and you stop to the value where x is getting closer and closer to. So x is approaching 2. All right. So it means that this is the limit. Okay, this is the limit. So the limit is at this point. Okay, because x is approaching from the left. Okay, from the left towards x equal to 2. So while you are tracing the graph, you have to stop up to this point. It means this is our limit. So therefore, the limit of the function as the function x squared plus 1 as x approaches to 2 from the left. So we are tracing the graph from the left towards x equal to 2. So this is our x equal to 2 at this point. So it means that this is the limit. So what is this? Alright, so if you look at the number, so this is the limit, which is equal to 5. So therefore, the limit here is equal to 5. Alright? And now we have to do the other one. So the other one is that we need to determine if the limit, or the limit of x squared plus 1 as x approaches to 2, but this time from the right. Okay, so we have here positive sign here. So it means from the right. Okay, so it means that we need to trace the graph. So we need to trace the graph. So trace the graph from the right towards the value x equal to 2. So it means that the direction of our tracing of the graph is coming from the right. Okay, so coming from the right towards 2, x equal to 2. So that means that we are going to trace the graph. Okay, so from the right, tracing the graph from the right. Okay, so from the right, okay, you can start from 3 going down, or you just extend it. It's okay, no problem. So from here, so tracing it down, and you know from one-sided limit as the values of x is decreasing, no? Decreasing. Pag sinabi natin if we say that right-hand limit, it means the value of x is decreasing. So you see from 3, we go to 2, and so on and so forth. Alright? So we have, and then we stop up to the value of x that is very, very close to 2, or approaching this 2. So it means that this is also the limit. And you see here that this limit is also equal to this one. Right? This is also equal to 5. So therefore, the limit of the function as x approaches to 2 from the right is also equal to 5. Okay? So therefore, since the right hand limit and the left hand limit, so this is our left hand limit, LHL, left hand limit is equal to the right hand limit. Okay, so since they are equal, you see this one, this is our left hand limit and this is our right hand limit. So we can say that the limit of the function x squared plus 1 as x approaches to 2 exists because they are equal. So it exists and the value is equal to 5. Alright, so the common value, or the value that the same value. Okay, I want to change the color. Well, first I have to erase this one. So it exists and this is equivalent to 5. Okay, so we have satisfied the second condition. So the function, the limit of the function exists. Now the third condition, so the third condition is we need to compare, no? We need to compare whether our f sub a is equal to limit of f of x. Okay, so we need to see this one. Okay, I have to change color. I just want to separate this one, class, so that you will not it won't confuse you. Okay, so I will separate this one. So we need to see if the limit of f of x as x approaches to a equal to f of a. Alright, so we have solved already. F sub a is equal to, what is this value? This is equal to 5, right? So in our first condition. that is equal to 5. And this one, we have also proven that it exists, and this is also equal to 5. Okay, so now we can say that f of a equal to the limit of f of x as x approaches to a. So they are equal. So therefore, we have satisfied the third condition also. So we can say that the function f of x as x approaches to the limit of the function of x equal to x squared plus 1 is continuous at x equal to 2. Okay? So I hope this is clear to you, class. So this is very important that you graph the function, something like this, so that when you say moving from the left, when you look at the left hand limit and the right hand limit, you just simply trace the curve going to the left, going to the right, and also, coming from the left and also coming from the right. You are tracing the graph, and you stop there, the value of x, which is equal to a, that is being approached by the uh, value of x. So what value is that? So in this case, we have x equal to 2. Okay, so I'll solve also this number here, the second question. We have some more numbers, and I want you to do it yourself. But for this one, just to add your example here, so I'll solve this one. We are given the same function, and now we are going to solve this problem. Okay, so to do that, I will use another screen. Okay, so we have the same given function, f of x so let's do it again. F of x so we have this given f of x equal to x squared plus 1. Okay, and then we are going to determine if this function is continuous at x equal to minus 1. Okay, so this is the second problem. So we know that we have drawn it already. I just draw it again roughly, what we have drawn a while ago, because we have the same graph actually. So we have the same function. Okay, this is our 1, 2, 3. So 1, 2, 3. You can even put 4, 4, 5, and so on. On the other side, we have minus 1, minus 2, and minus 3, and minus 4. Okay, so we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have 10. Okay, this is our x-axis. This is our y-axis, where y is a function of x. So y is a function of x. y equal to f of x. Okay, and then we have a table a while ago. We have x here, and we have f of x, and we have tried values for x and solved for f of x. Okay, so we have to draw the table first. Okay, so when we have x equal to minus 3, okay, so we already calculated this a while ago. This is 10. Alright, so when we have minus 2, so minus 2, so we have 5, we have minus 1, so we have 2. Now you just substitute it here. And when this is 0, so this is equal to 1, and this is 1, we have 2, and we have, when we have 2, so we have 5 here, and when this is 3, so we have 10. Okay, so we use the same table. Alright, so again we'll graph it as when x equal to minus 3, f of x equal to 10. Okay, so just project upward. So this is our, okay, I'll use another color. Okay, so this is our point. This is for x equal to 3, f of x equal to 10. When x equal to minus 2, sorry, x equal to minus 3, f of x equal to 10. When x equal to minus 2, we have f of x equal to 5. Okay, so at this point here, when x equal to minus 1, we have 2. When x equal to 0, we have f of x equal to 1, so somewhere here. When x equal to 1, we have f of x equal to 2. When x equal to 2, x equal to f of x equal to 5. And x equal to 3, f of x equal to 10. Okay, somewhere here. Okay, so tracing the, or connecting the points, we can trace the graph. Right, so let's trace or connect the points. We have here, so actually our graph is a parabola, opens upward. Okay, so you can extend this one and just put an arrow. And same with this, you just extend it and just put an arrow. Okay, so our so we have to test, right? We have to test. Number one, we have to find out if f sub a exists. So f sub a, does f sub a exist? Okay, so what is our f sub a? Our f sub a natin is, this is our a. Okay, so we have to determine the value of f sub a. So f sub, so this time we have a is negative 1. Okay, so what is f sub negative 1? So f sub negative 1 is equal to, you just substitute it here. So when this is negative 1, so negative 1 squared is 1 plus 1. So we have equal to 2. Okay, now the second condition that we need to satisfy is if the limit, or we have the limit of the function, so the limit of f of x, so we have to see if this, as x approaches to a, if this one exists, right? Or our given function, so we have limit of, now you can write limit now, or you just put lim. Okay, so limit of f of x, or f of x is equal to x squared plus 1. Uh, so this is x squared plus 1. So we have to determine if this one exists as x approaches to. So our x this time is equal to negative 1. Okay, so to find out if this one exists, okay, so does this exist? So this is still questionable. Does it exist? Okay, so we have to find out, right? Okay, so to find out, we have to find the left hand limit and the right hand limit and compare if they're equal. So the limit of x squared plus 1 as x approaches to negative 1, and this time from the left. Okay, so we have here negative above the number 1. Okay, so from the left, so it means that we need to trace the graph. We need to trace the graph from the left towards where? Towards x equal to minus 1. So where is this x equal to minus 1? Alright, so this is x equal to minus 1. Okay? Sorry, we have to hit 1 here. Okay, this is x. Okay, so we have to trace the graph from the left. Okay, so it means from the left. So this is negative, it means from the left. So tracing the graph from the left towards x equal to minus 1. So it means up to this point. So what is the limit? So the limit, this one at this point is this value. Okay, so this is the limit. Alright, so it means that the limit, or the left hand limit, is equal to 2. Alright, now the other one is we have to find out the limit of x squared plus 1 as x approaches to negative 1, but this time from the right. Okay, so we have here plus. Okay, so from the right. So plus there indicate that the tracing of the graph is from the right. Okay? So it means from here, from this part of the graph, you trace from the right towards -1. Okay, so from here, you go down, you trace it down. Okay, and then you see that the value of x here is decreasing, right? And then you stop where? Up to x equal to 1. Sorry, so this is x up to 1. So here, so you stop at x equal to 1. This is the value of x that is being approached to when we trace from the right towards x equal to 1. Okay, so you stop up to here, stop to here of our graph. So it means that this is our limit. Okay, this is our limit. So what is this value? Okay, so that value is also this one. So therefore, the limit here is equal to 2. Okay, so now we have proven that since the left hand limit, this is our left hand limit, LHL. So LHL stands for the left hand limit. Our left hand limit and the right hand limit matches or are equal. Okay, so they are equal and both equal to 2. So therefore we can say that this limit of x squared plus 1 as x approaches to -1 exists. So we asked a while ago if it does exist, then the answer here is yes, it exists. So we can say that yes, it exists because we have proven that the left hand limit is equal to the right hand limit, this one. Alright, so it exists. It means that we have satisfied condition number 2. So a while ago, we have satisfied condition number 1. Now, next we have to satisfy condition number 3. So what is this condition number 3? We have to compare. We have to compare the value of f sub a, or value of the function, and the limit of the function. Okay, so what is the value of a function? We have value of a function is in our condition we have f sub a. All right, so the question is, does it or is it equal to the limit of the function? Limit of the function of x as x approaches to a. All right, so that's the question, as x approaches to a. Okay, so that's a question. So this is questionable. Okay, now our f sub a. So our f sub a is simply, okay, so you have f sub a here. Our f sub a is simply f sub our f sub a is simply f sub, what is our a for this problem? This is minus 1, right? So thus f sub -1, is it equal to the limit of x squared plus 1 as x approaches to -1. Okay, so we have proven that the limit exists and that is equal to 2. Okay, so this one is equal to 2, and f sub -1, we have calculated this also equal to 2, right? So we can say that both, f sub 1 is equal to f sub 2. So therefore, we have yes. Okay, so this is yes. Okay, so the answer here is yes. So they're equal. So therefore, we can say that, well, this is our conclusion. So our conclusion here is that, so we have here therefore This is the abbreviation of the word therefore, class. So when you make a conclusion, so therefore, since all the conditions are satisfied, all the conditions are or were satisfied. Okay, so satisfied. Let's check this one first. So we can say that the function is continuous at x equal to minus 1. Okay, so therefore, the function, meaning f, uh, the function is continuous. F is continuous 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 at x equal to minus 1. Okay, so is it clear, class? I hope you understand this one. So if you understand this one, class, there's no problem. You can easily solve the other exercises. All right. So to continue, so let's continue to the next page. So the next page or the next slide. So we have here another problem. So this rational function. You just try it yourself, class. The technique here is assume values for x and solve for f of x, and after that you graph. Okay, and then you just satisfy that. You just check whether those three conditions were satisfied. So if those conditions were satisfied, then your answer here is continuous. No? F is continuous at x equal to 2, and the other one is also continuous at x equal to minus 1. Otherwise, so the function is discontinuous at this given values for x. Okay, so I will not solve this one. You just practice this number as well as this number. Okay, so and then I will proceed to another slide. Okay, we have here a polynomial function is continuous at every real number. A polynomial function is continuous at every real number. So still remember what is real number? You just review what's a real number so that you can fully understand what does it mean. This statement here, continuous at every real number. So real number composed of, we have the positive, negative whole numbers, and so on and so forth. Okay, so I'll change the color here. Alright, so for example, if you have this function, f of x equal to x squared plus 2x plus 5, so it means that for every values real number that you are going to substitute into this expression, then you will always get a corresponding f of x. So continuous. Now the function is continuous. So the best way is to graph this function. Again, you have to let any values for x and then solve for f of x. And then you plot the points, connect the points, and there you have the graph of this function. So this one is continuous at every real number, polynomial. So another theorem, a rational function is continuous at every number in its domain. So what is domain, class? So you know how to find the domain, right? So you know how to calculate the domain. And then it says that rational function is continuous at every number in its domain. So there are values, for example, if that is fractional, like in the previous slide, so you have x minus something there, x minus 4. So it means that the domain is all real numbers except 4, no? The value of x that can make the denominator equal to 0. Okay? So rational function is continuous at every number in its domain. So the function something like this, f of x equal to x plus 5 over x minus 4. This is a rational function. So this function is continuous at all values of x, meaning real numbers, except x equal to 4, because when x equal to 4, this makes the denominator 0. So anything or something divided by 0, as mentioned before, that is undefined. No, we cannot determine what is that number. Okay, so discontinuous at that value of x equal to 4. Okay, so in other words, this function is continuous at x equal to 1, right? When you substitute x equal to 1 here, you get the value of f of x. When x equal to 2, then substitute the values here, x equal to 2, then you have the value of the function. But if you substitute x equal to 4, so what will happen? So x, which is equal to 4, so 4 minus 4, this becomes 0. So it is continuous at every number except at x equal to 4. So in this case, okay? Next, geometrically, so we have a definition of continuity. So this is just an informal definition that a continuous function is one whose graph can be drawn without the pen leaving the paper. So it means, class, if this is the pen, and if I draw something, so if I draw something like this, okay, I will not left the pen. So this is a continuous function. But if you draw something like this one, and then somewhere you lost, okay, or there's a cut, then you continue something like this. So this is a discontinuous function. Okay, so at this point, so discontinuous function is discontinuous at this point. Alright, so this is the geometrical explanation of continuity. So that is one with no holes or gaps. We call it continuous function. But if you can see, there's a hole or something, a gap, something like this, and then there's a gap. So this is a discontinuous function. Okay, so I hope it's clear. Now there's a very clear example here. This is an example of continuous function or continuous graph. So you draw this graph, okay, you trace this graph, something like this, and you did not bring up the pen, okay, you're just tracing it. So this is an example of continuous function or continuous graph. Okay, another example here, geometrically, we have here a line. Okay, so we have here a line. We're given the limit of function of x as x approaches to 0. So we determine that the value of f sub 0 is equal to 1. Okay, so this is meaning in our previous discussion, so the limit exists. Okay, so the limit exists at where? At x equal to, or f of x equal to f sub 0, which is equal to 1. So this is a continuous function. Okay, so continuous at x equal to 0. So even if x equal to 0 here, so this is continuous because we have proven that the limit of f of x as x approaches to 0, the limit is exists. No, if you trace the graph from the left, okay, and you have this limit. If you trace the graph from the right, you have this limit, and this limit is the same, which is equal to 1. So it exists. So therefore, this is a continuous graph or continuous function. Alright, now another geometric explanation of continuity. So here are the three graphs that will tell us that the function is discontinuous. So in these cases, so we have functions discontinuities at x equal to c. So let's start with the upper one. So this is c. So see, this is the value where x is approaching to. Oh, alright. So when you are tracing, so we are tracing from the left. Oh, remember limit, no, limit from, or limit of the function, limit of f of x, a limit of f of x as x approaches to as x approaches to C, right, from the left. From the left, it means that you need to trace. Change this. You need to trace the graph. You need to trace the graph from the left. Okay, tracing the graph from the left, something like this. Okay, so you're going to. It means you're moving. No, you're approaching. Meaning the value of x is approaching towards C. All right. So you find out that you see here. If you continue this one, the graph will just go on and on and on and on. It will not stop. So there's no limit, right? And it cuts. No? It cuts somewhere here. No. All right. And if you are going to trace the graph from the left, no, you're tracing the graph from the left. So it means that, sorry, from the right. So it means that you are trying to find the right hand limit. So the limit of the function of x as x approaches to C. Okay, so as x approaches to C. So this time from the right. So positive here indicates from the right. Okay, so trace the graph from the right. So our value of x is decreasing, but our f of x is increasing. But we cannot determine, no, what's the limit. All right. So we can say that f sub c is not defined. So f sub c not defined. We cannot define the value because if you substitute the value of x, which is equal to c, so your f sub c is not defined. No, this is undefined. So undefined. Okay, so this is undef or undefined. All right. Now looking at this other example. So again, this is our C. This is the value of x that is where x is approaching to or getting closer to. Okay, now if you take the limit, once again, limit this one to prove that the limit exists. So you have to look at the left hand limit, meaning the limit from the left. No, you trace the graph from the left. Okay, so tracing the graph from the left, right, from the left. Okay, so we have here the limit. So this is the limit. You just project horizontally towards the y-axis. So this is the limit. So at this point, we have a value here. This is the limit. All right. Now, if you take this limit of a function as x approaches to C from the right. So from the right, so going towards C from the right. So a while ago, we're tracing the graph towards C from the left. So it means for this part here, you just forget this one for a while. Just focus your attention here. So trace the graph from the right, okay, and going towards this point, and it stopped from here. So this is the limit, okay. So you just project a horizontal line to the y-axis, perpendicular to y-axis, and this is your limit, okay. So we can say that both limit exist, but if you compare, you see this value is less than this value, so they are not equal. So we can say that the function does not exist. So if the function does not exist, it already uh, it didn't comply, it did not satisfy the second condition. So this makes this uh, function discontinuous. Okay, discontinuous at C. Okay, so is it clear, class? And now the last graph here. So on our last graph, we have, okay, I'll change color once again. Okay, so taking into consideration this graph, so once again, this is our C. This is the value where our x approaches to. Where our x approaches to. So again, we have to find the limit of f of x as x approaches to c from the left. So from the left meaning we have to trace. Okay, so from the left. So going to c from the left. It means that we have to trace the graph from the left towards this point that corresponds to x equal to c. So this is the limit. Okay, this is the limit. And this is equal to this. You just draw a line perpendicular to the y-axis, and then there you get the limit. So whatever is the value at this point here in your y, which is equal to f of x, so that is the limit. Right? This is our L. Now, tracing the graph from the right towards C. So from the right towards C. So it means you focus your attention here. Okay, so I'll change the color. I'll use this green one. Okay, so tracing the graph from the right towards the value of x that is equal to C. Alright, so tracing it towards the left, going to C. Okay, so and then it's jump up here. Right, so it's not here, it's disappear, but it goes up. So that's why you have a point there. Okay, so while you are tracing the graph from the right towards this point, so it jump up here. Okay, so this is now the limit of this graph. So this is, you can call it as M. Alright, so the limit the limit of the graph when you're tracing from the right towards this value where that corresponds to x equal to c. So the point at this part of the graph jump up here. So we have the limit. We call that limit as M, or you can use any later. You can use L, L1, and use L2 here, or L1 here, and then use L2 here. So it doesn't matter. So what is important is that you just need to compare the left hand limit, and the right hand limit. So the left hand and the right hand limit, as you can see, so they are not equal. Okay, so the left hand limit is not equal to the right hand limit. You see, this one is higher than this. So therefore, the function does not exist. So the second condition, once again, is not satisfied, or was not satisfied. Okay, so I hope everything is clear, and I would like to stop my discussion here because it's very long already. I'll just make the second part of this topic continuity. Alright, so thank you very much. Have a nice day, everyone, and stay safe and healthy always. God bless, and bye for now. See you in the next video. Bye.